we are going to start with the proof of the direction from 2 to 1. This direction is a very hard direction, which involves a lot of lemmas. The proof that we are going to follow is taken from the book An Introduction to Defining Approximations by Castles. This is published in the year 1957. And the proof of this direction involves a lot of lemmas, which we are going to develop one by one. And I should make it clear that this is in the chapter 3, section 5 of the book. Okay, now let's start developing this proof. The first lemma that I'm going to introduce is an equivalent form of the theorem for the direction 2 to 1. And I will give it a name, call it key lemma. However, I should remind you that the author didn't call it key lemma in the book. I call it key lemma so that it will be easy for us to refer to this. Okay, let me state it. Let A be an n by n real matrix and B be a vector in Rm such that whenever you have a vector u in Rm and u transpose times aq minus p is an integer for any p in Zm and q in Zn, we have that the u transpose times p is an integer. Given this hypothesis, notice that this hypothesis is given by an implication. Then, for any epsilon greater than 0, there exists p in Zm and q in Zn such that we have this inhomogeneous defining approximation. And this part is same as the statement 1 in the Kronecker theorem. So the goal of this lemma is to replace the statement 2, namely this statement in the Kronecker theorem, with this guy. Why this key lemma is equivalent to the direction of the Kronecker theorem from 2 to 1. And let me explain to you why this is true. I believe that most of you should be able to check this by yourself. This should be very straightforward to most of you. So you might want to pause this video and think about it on your own for a while. But I will give you the proof anyway. Okay, now let's first prove the forward direction. We're going to assume that the pair A and B satisfy the statement number 2 of the Kronecker theorem. And we assume that the key lemma is already proved. In order to use the key lemma, we need this assumption. And to this end, we need to assume this part holds. Namely, we want to assume that whenever u is in Rm and ut times aq minus p is an integer for any p in Zm and q in Zn, we have utb is in Z. And to this end, it suffices to show that atu is in Zn and u is in Zm, so that we can use the statement 2 of the Kronecker theorem to conclude that utb is in Z. And by the key lemma, we conclude that we have this inhomogeneous defining approximation, which is precisely the statement number 1 in the Kronecker theorem. That is the logical relation in this proof. There's nothing tricky to prove this equivalence, as long as you figure out the logical relations of those hypotheses. So, how do we get this? By setting q equal to 0 and make p equal to ej, which is the jth canonical basis of Rm. So here j is from 1 to m. We have the jth component of u is an integer. So u is an integer value vector in Zn. That verifies this part. For this part, we use the same trick by setting p equal to 0 and make q equal to ei, where I is from 1 to n. We have the ith component of uta is in Z for any I from 1 to n, and thus uta is in Znt. I put a transpose here to emphasize this is a row vector. So equivalently, you can say atu as a column vector is in Zn. Now, by the statement number 2, you conclude that utb is in Z. So, by the key lemma, you have the number 1 of the Kronecker theorem. That finishes the forward direction. The backward direction is actually easier. Now suppose the pair A, B is such that whenever U is in Rm and Ut times Aq minus P is in Z, whenever P is in Zm and Q is in Zn, we have UTB is an integer. This is the assumption of the key lemma, namely this part. and we want to get the conclusion of the key lemma. And we also assume that we have the implication 2 to 1 for the Kronecker theorem. So the goal this time is to verify the hypothesis, namely the statement number 2 of the Kronecker theorem. We're going to assume this part and try to get this part by using this assumption. So then, if we assume that ATU is in Zn and U is in Zm, we have UT AQ minus P, which is UTA times Q minus UTP. Now, whenever P and Q are integer valued vectors, because this part, by our assumption, is integer valued, this is a transpose of this. And U is also assumed to be an integer valued vector. So this part is also integer valued. So the whole thing is an integer whenever P is in Zm and Q is in Zn. Now, this hypothesis is satisfied. So by our assumption that we get UTB is an integer. So by our assumption, UTB is in Z, which means whenever U is in Zm and ATU is in Zn, we have UTB is in Z. That is precisely the statement number 2 of the Kronecker theorem. And now by the Kronecker theorem, the direction from 2 to 1, we have the statement number 1, namely, for any epsilon greater than 0, there is P in Zm and Q in Zn such that the maximum norm of AQ minus P plus B such that the maximum norm of AQ minus P plus B is less than epsilon. And this finishes the proof of the equivalence between this key lemma and the Kronecker theorem, the direction from 2 to 1.